Hello, everyone. This is Wenbin from Shandong University. Today, I'm going to introduce our work, HiDPU, a DPU-originated hybrid indexing schema for disaggregated storage systems. In modern data centers, the data processing unit is replacing the traditional network interface card to handle communication with computing servers. By integrating computing, networking, and storage capabilities, the DPU acts as a smart and programmable processor on the data path, with the potential to accelerate data processing and reduce CPU load. For example, upon receiving an IO request, the DPU can first retrieve the physical device address from the storage controller in the CPU side. It then constructs the PCIe command to directly access storage devices. In this way, redundant data copy between CPU memory is removed, and the data efficiency is improved. However, in this procedure, the CPU is still involved to translate addresses. In the storage server of a disaggregated storage system, CPU resources are limited, and involving CPU computing also brings associated overhead. When processing massive concurrent I/O requests, the latency of this CPU-centric address translation can be high. So our motivation is to offload the index of mapping table and do address translation in the DPU. However, there are several challenges for indexing in DPU. First, the DPU memory is extremely limited compared to the size of mapping table. On this stage, DPU must store most of data in the host memory, but interaction overhead through PCIe DMA could also be high. Besides, SO has many cores for processing concurrent work. Each core of DPU only has a limited computation power. To address these challenges, an efficient index structure is essential. We start our work by exploring current index structures for storage mapping table. Multi-level page table is faster, but better at space efficiency due to its inherent hosts in each level of subtables. Learned table constructs learned indexes on mapping table to achieve better space efficiency, but it requires extra local search due to the prediction inaccuracy. Perfect hash table offers both good lookup and space efficiency, but it doesn't support real-time index update and incurs high reconstruction overhead. So unfortunately, there is no current index designed for DPU and could effectively address these challenges. In this work, we propose HiDPU. It is composed of three main components. First, a hybrid index includes an inner index that fits into DPU's limited memory, while the outer index is optimized for efficient searching. A DPU offloaded cache is employed to further reduce unnecessary interactions with CPU memory. At last, asynchronous index update strategy supports processing complex index update operations in the CPU and ensures DPU focuses on simple but frequent index query. We start introducing the detail of the HiDPU by hybrid index. The hybrid index is composed of a learned index and continuity-based segments. First, a segmentation algorithm divides the mapping table into fixed segments. HiDPU will create different indexes for segments with different levels of continuity, except of accurate segments. Perfect hash table-based segments have secondary hashing parameters called pilots as outer index. Next, a learned index is built with the first key of each segment. Segmentation and the learned index make sure the size of inner index can adjust to the constrained DPU memory space. To find the corresponding mapping entry of a logical address, HiDPU first determines which segment it belongs using learned indexes. If it belongs to an accurate segment, the target position is get with the base address and an offset. If the logical address belongs to a PTHash segment, HiDPU will first retrieve the pilot value through a hash and a DMA operation, then perform a second hash with the pilot value to find the conflict-free target position in the mapping table. The linear-based PTHash segment works similarly with PTHash segment, except that the pilot position is determined through a division operation instead of a hash. For aggregate segments, one DMA is already sufficient to fetch the mapping entry, but for PTHash and LPTHash segments, an extra DMA is needed to get the pilot value. To address this, HiDPU introduced a pilot cache in DPU. It uses optimistic locking, which loads the entire cache group into thread's private space and compare the IDs to find the right pilot value. Before updating cache, it will check the group counter to find the next writable position in the cache group, which helps preventing write conflicts. Besides, LPTHash utilizes the segments with considerable continuity to group adjacent keys into a bucket and share the same pilot value. Experimental result shows this could effectively improve the hit ratio. In HiDPU, DPU handles simple and frequent read operations, while complex and critical index update caused by write operation is handled by CPU. Write operation may require mapping tables update, delete, or insert. The first two can be done in place within the mapping table, but insertion might lead to the index reconstruction. To address this, new insertions are stored in a Kuku hash-based buffer, which also allows DPU to check the latest key with one round of DMA. When the buffer fills up, local reconstruction is triggered to rebuild the segment index. The buffer will be first divided into each segment according to the segment's first key, and each segment's reconstruction is independent with others. The version number in segment metadata help to identify the expired cache entries. Note that local reconstruction doesn't require updating the learned models and won't affect queries for other segments. HiDPU will only update learned models during global reconstruction, and it is invoked during the system idle. We have implemented a HiDPU prototype on a Huawei DPU. It has 4 megabytes of internal memory shared by all threads, and each DPU thread is also equipped with 4 kilobytes of private memory. We have also implemented several optimizations in the DPU to increase the efficiency of processing learned indexes. They include fixed point model calculation, pipeline-based local search, and data reuse. For compression, we implemented two baseline indexes, DPage and dlearned. DPage is a three-level page table with the first level offloaded to the DPU. Dlearned builds learned indexes on the mapping table and adjusts the error bound to try to make sure that the learned indexes can be offloaded into DPU memory. Above optimizations of learned index are also applied to the dlearned. Workloads used in the experiment are from two sources. The first is Microsoft Research Cambridge block I/O traces, and the second comes from the real-time I/O requests captured from a Fumio-based server running various real-world applications. This table shows the scale of traces. We have also open-sourced a functional CPU version of HiDPU. It doesn't rely on DPU and simulate all operations of HiDPU with only CPU instructions and host memory. Overall performance shows the throughput and average latency with different number of clients. DPage always needs two random DMA operations for each query, making it less efficient. For dlearned, when address continuity is high, it only requires one single DMA to fetch the predicted mapping entries into the DPU, which makes it more efficient than DPage. However, when the address continuity is low, it needs to fetch more data into the DPU memory and perform the local search to find the correct position of the target mapping entry, which also reduces its efficiency. With the help of palette cache, HiDPU has more than 92% probability to obtain the target mapping entry with only one DMA operation, which gives it the best performance among all traces. As a result, HiDPU can achieve a minimum of 1.5 times to a maximum of 6.3 times performance improvement. The DPU memory usage of all indexes are already constrained to within 4 megabytes. Here we present the CPU memory overhead of different indexes. The memory overhead of DPage comes from its host in each table, and dlearned has to store the logical address along with its mapping entry for local search. Space overhead of HiDPU mainly comes from its perfect hash table. It treats off the complexity of index construction by allowing acceptable hosts in the mapping table. As shown in the figure, HiDPU shows stable and the lowest memory overhead across all test traces. One exception is Trees project, where DPage has lower memory overhead because this trace is mainly composed of large files, leaving few holes in the page table. We then expanded the test set to the petabeta scale storage to test the scalability of all indexes. With the extended trees, both DPage and HiDPU successfully construct and offload their indexes into DPU. However, the number of hosts in DPage also increases as the dataset grows, leading to significant CPU memory waste. On the other hand, as the dataset expands, dlearned quickly fails to construct learned indexes that could be offloaded into the DPU. We then evaluate how index reconstruction impacts the performance of HiDPU. Since the local reconstruction is conducted in the background, it won't block the index queries. The only effect is that it may cause cache expiration. As shown in the figure, when local reconstruction occurs, the pilot cache may experience expiration and misses. But thanks to the LPTHash segments, the reduction in cache hit ratio caused by expiration is no more than 10%, and the overall performance degradation is negligible. We also compared HiDPU with the recent learned FTL, which accelerates queries using a cached mapping table and learned indexes. Unfortunately, learned FTL struggles to be offloaded to the DPU because of its fixed size bitmap, which requires 1 bit for each possible mapping entry. Therefore, for fair comparison, we also implemented a HiDPU version that runs entirely in CPU and owns the memory, which is referred to as HiDPU-H. We also make sure the HiDPU-H has the same host memory usage with learned FTL. Since the HiDPU-H and learned FTL run on the CPU, they both incur the overhead of involving CPU for each query, which significantly degrade their performance. In this work, we explore the use of DPU to accelerate the data path in disaggregated storage systems. Without indexing, the DPU still relies on the CPU for address translation, which adds extra overhead. And overloading the index to the DPU facing challenges such as limited space, interaction overhead, and low computation power. To address these challenges, we propose HiDPU, which integrates techniques to overcome each of these issues. We have also implemented a HiDPU prototype on a real DPU and evaluated its effectiveness. This is all about my presentation. Thank you for listening. For more details about this work, please contact me by the underlying email address. I will be happy to answer any questions you may have.